in the core communication technologies, right? With a focus on physical layer. So this is what I'm going to share today. So first, we'll share that evolution of wireless communication networks to AI native 6G. So what we really mean by AI native, and then we will take two aspects of AI native. One is AI for network, and another is network for AI. So AI for network, as an example, we'll try to find out that what all areas at the core physical layer, which is the basic of any communication system, AI is being used, and across the world, to some extent in India also, but majorly across the world, people are working on it, and industries are also investing a lot on it, and why we need to do that. And the next thing is that how network for AI is going to usher in a new paradigm of called semantic communication, which is very new for 6G, although the some of the core subjects that they use or that they leverage are there for about a decade. So let us have a very brief overview of evolution of wireless communication networks to AI native 6G. Now, how do we see wireless communication? In 1980s, we had 1G analog voice. We hardly had anything like that in India. We started to feel the true sense of mobility from late 90s with the advent of mobile phones. Before that, we had pagers. So we had digital voice and SMS. It started to the infrastructure started to float around the world from 1990s, and then we had something called 3G. So 3G, by 3G we got mobile internet, we had multimedia, and the advent of smartphone. So if you remember, at least for India, since 2020, we had this upsurge in propagation of smartphones, right? And since 2010, 4G, it started to penetrate the smartphone market, and with the smartphone, internet effectively came into our pockets. Earlier, we used to, internet carrying internet with yourself while moving around was not a possibility. You had to either sit on a desktop or on a laptop, that is a workstation, any kind of workstation, and then you connect to the internet. But then we have this broadband, and video streaming became the killer use case. We started to do Netflix and all, and then we have 5G, and now we are talking about 6G with a vision for 2030. So why we evolved? I mean, fundamentally we still talk, right? We talk over any telecom network. So we have some growing demands. So firstly, the demand was for more speed. And why more speed? I'll come to that. Then, of course, the fundamental thing is connectivity. More people want to join because we have a upsurge in number of subscribers. And then today, what we are also expecting is intelligence. So the network should carry intelligence along with us, and around, right? Right. So let us try to understand this a little bit, little bit in detail, that why what actually drove these transitions. So from 1G to 2G, we basically wanted more clear sound, more more with the advent of digital communication and the digital signal processing, etc. We could find that we could make our signals more secure from tampering, from eavesdropping, etc. um, and then, so it actually, this 2G is still reigning even today. We have the fundamental, the 2G is still there. But then we had the rise of 2G to 3G, because when we had this multimedia and all these services available over the internet, then the idea was that um, that why we cannot have the internet, like the when we had this more spread of emails, more spread of chat kind of applications started to come. So the idea of that people should be connected to the internet even when they are moving. So this idea was not a reality even in our country, even in 2003-4 time, right? And when we started to carry the internet in our pocket with 3G, so along with that, in increasing rise in demand for high-speed data, okay, that started to flow. Now, this demand for high-speed data was basically, was basically aided by the increase or the sophistication in streaming technologies, video streaming technologies. So they had more sophisticated video streaming technologies, and then along with that, more business models started to float in. So that is why we had this demand for high-speed data, and because we need to stream video in HD, so 3G to 4G transition started, and that actually became the real killer use case or killer application for smartphones, because if the earlier versions of phones were not really were incapacitated in terms of showing the videos. They are not up to the good comfort to the users. Now the thing is, from 4G to 5G, we have a different kind of paradigm shift, even in the model in which we expect. As a consumer also, the pattern is changing. So the pattern is, till 4G, we had something called B2C, which is business to consumer. So there is a service provider who is providing you the service, and you are a consumer, you are consuming the service. Maybe you are watching Netflix video, maybe you are doing an email, you are watching some videos in YouTube, you are doing Facebook, Twitter, etc., social media, multimedia, and all these things. But then 4G to 5G, we had an explosion. It is still not there, but we had something called IoT, right? So Internet of Things started to almost, pick up the pace from 2010, and we had the requirement of connecting IoT devices over a low power network across a wide range of area, and the smart city and all these ideas started to come. Smart transport, smart vehicles, smart factories, and all this smart world. These concepts started to come. Along with that, there were a lot of innovations in AR, VR. So all these, Meta and Apple and Google, all these companies started to experiment with these VR glasses, etc., and robotics. So what essentially it's a varied kind of devices that started to connect together, and we are still living through this era. This era is not yet. We are still unfolding. We're still trying to see what is there in store. It is not yet ended. And then we had 5G to 6G, the transition that we are right now talking about. It is not yet there. It is a future. And that is why it should be important to faculties and researchers for who are opting to contribute to the future. Now, this is a completely different world we are uh, viewing, where you must have heard about metaverse and all these ideas. So here the idea is basically that the digital and physical should meet together in a way that you can, I mean, just imagine like Matrix movie. So you have a digital self as well as a physical self. Your environment has a digital self as well as a physical self. And so there is going to be a physical and digital continuum to making this world, a composite, you know, making this world a completely, you can say that living in the world, living in the what you call science fiction, to make that a reality. Now, whatever we talk about, be it I mean, it needs immense development in computer science. It needs immense development in terms of algorithms, in visual computing, in AI, and everywhere. But at the core of it, as we move and as we talk about more and more of these kind of applications, more and more we feel that without the network nothing can actually work. So telecom holds a very important role, and it holds a very important role in terms of commercial success of these kind of applications. Now, having said that, let us try to clarify one concept. Like, as you have seen that we have been, if I go back to this slide, so if you look at it, the we have a fatter pipe, right? Moving towards 6G. So the arrow is becoming, larger and larger and larger. I mean, fatter and fatter and fatter. So from 50 kbps to 20 mbps to 1 gbps to 20 gbps to 1 terabyte tbps, right? um, so so having said that, the problem that we see is a fundamental understanding while we are talking about all these tbps, gbps, mbps, kbps, everything. Is it only a fatter pipe, right? So 3G, 4G, 5G, 3G had a, a little bit fatter than 2G. 4G is a bit more fat than 3G, and 5G is a bit more fat than 4G. So fat by fat, I mean it is like you have more number of bits or more number of data that you can pump in. If that is what we are looking at, the answer is no. From 5G, there has been a paradigm shift in the way we look at communication. Why? Because 5G does not only talk about high bandwidth. Well, whatever data rate or bandwidth, whatever you see, that data rate or bandwidth is the peak that it is going to support. Of course, it has to be there. But on the fundamental concepts from which 5G started was like this triangle, where on one end it had services like enhanced mobile broadband, which will have like AR VR games, then high definition 8K video transmission, uh, along with that immersive experience and all. And then we had ultra reliable and low latency. That is completely another end. So smart vehicles, robots, you need to send just a single command, but that command has to be sent within a certain SLA, right? It should not fail that latency. It should not fail that quality. Okay, you can't tolerate a glitch over there because you're doing a critical operation. So that is a completely different kind of requirements. The other thing is massive machine type communication, and that is basically what is IoT. So in IoT, when we are talking about making a internet of things in reality, that means just like humans are contributed to the internet, now things are going to be contributed to the internet, and a true smart world can only be created by when everything in our surrounding has a voice. And how is that possible? It is possible through sensors. You can put pressure sensors, you can put temperature sensors, you can put weather sensor, moisture sensor, you can put device fault sensors, any kind of sensor, right? You can put home sensors, you can put theft alert sensors, so many things. And all these things have to in a concerted manner, they have to all connect together, and these are millions of devices per square kilometer. That is the vision. Now this talks about capacity in terms of how many devices can a network operator, how many devices can be allocated, the resources to connect or to talk. I mean, if you imagine the GSM days, so in those days, what we used to have, during New Year or during, like Vijayadashami or Diwali, what we used to have is that I mean, you were actually effectively barred from sending SMS or greetings SMS. Why is that? Why it was like that? Because the operators, given the technology of that day, were not able to, cater to all these users, right? Now, um, so because the technology did not support this scale of capacity. Again, we had CDMA based 3G systems, then 4G systems. We had a huge number of smartphones connecting over the internet, connecting to the base stations. We have a lot of capacity gain. But when we are talking about machine type communications, we need to understand one thing, that these devices are not sending huge data, right? They're sending small amount of data, if maybe a few kilobytes hardly, 1 kilobyte, hardly 1 kilobyte, mostly within a few bytes. But that has to travel within a certain latency. It cannot delay. That has to, and all the devices, whenever they want to connect, they have to connect, because all the sensor data that has a critical lifetime. It is not like email. An email, I can respond to an email maybe after 1 day or 2 days, right? But for sensor data, the time is very critical. It has a lifetime. If the life of the sensor data is dead, then is gone, then the sensor data loses its value, its importance. And apart from that, what you do with all this sensor data is you process them, you do the analytics, you get the inner meaning of what this data is going to tell you. And from that intelligence, what you do is you actuate, right? You take decisions, you actuate certain devices. It may be another IoT device based on the for example, based on the time sensor. You can actuate a coffee machine, right? So this way the devices are going to talk. Now, one thing that is important over here is that in terms of quality of service, all these are different. All these are different in terms of how much what is the quality of service demand that they have. Now, apart from that, there is one important shift that we have here. uh, just give me 1 second. So, one important thing is that this is the first time from 5G we had this merger of two streams. One is computer science and telecommunication. Because with 5G, we started to have more and more, adoption of intelligence into the network. At the same time, we became more and more cloud native, and we expect the developers, the application system designers, the system integrators, they expect an availability of computing stuffs that will be imbibed within the network. So there are two things. One is all these things, all these, the different, vertices of this 5G triangle, they have different quality of service. Unlike previous generations, 4G does not support IoT. It is not energy friendly. It is not, bandwidth efficient for IoT communication. 4G may support some form of mobile broadband, but it will not support reliable low latency communication for robot control. The kind of latency you're talking about, okay? So 5G comes with a common umbrella of technologies from which there will be some basic services, but from that you can derive, based on your QoS requirement, the way you want it, the network can be made to behave like that. So this is a new thing that made a total paradigm shift from 5G. And with the merger of, computing came into 5G, because 5G came up with this concept of mobile edge computing, or MEC, or you can simply say network edge computing, or you can say multi-access edge computing. So there is some computing resource that is close to the user equipment residing nearby and supporting, right? So when we are talking about the quality of service, so in 4G we had something like quality of service guarantee, right? And but then in 5G we talk about network slicing. So we can understand this with a very simple example. So in 4G, if you are a highly paid customer, or you are consuming some type of data which the operator wants to prefer to have a more efficient routing, to have more better resources, etc., then it is the bearer service remains the same, but depending on what type of packet it is, and for the kind of service, what type of packet it is, which user is sending, so the bearer can actually within the jungle of all the packets can identify, pick and choose, and then put them into hierarchy OS. So it is just like you have a common road, very wide road. Consider this like a broadband communication, and you have an ambulance passing through. Now there are vehicles passing in two lanes. Now, if an ambulance comes there, it will request for privilege because it has to travel faster. So what has to happen? Traffic police, which is the network operator, you just consider the analogy of network operator. The network operator will have to jump in as traffic police, and it has to single out ambulance, and then it has to penalize, or it has to make others sacrifice to find a way for the ambulance, so that the ambulance can travel faster, right? So uh, our ambulance is getting priority, but you just look at the complexity or the hazardousness. So there is a jungle of traffic, and from there you are spotting the ambulance, then you are arranging, you're segregating the traffic, you're making way, and then you're pushing the ambulance through that, maybe through the wrong lane. In case of 5G, what we can have is enterprises or typical users, it may be government users, depending on certain applications, we can, the enterprises can actually demand for a dedicated virtual network within that common shared space. Okay. So it is like here also ambulance gets a priority, but for ambulance service, there is a dedicated lane already created. So if you look at the end-to-end latency, because of the QoS management, that is managing the traffic, letting the ambulance go, and all these things, because of all these QoS management and all, the latency or the time taken to traverse from patient's premise to the hospital by the ambulance in the left hand side picture, and given that there is a dedicated way for the ambulance to proceed and no one is going to occupy that, uh, so you can readily understand that the right hand side will have much lower latency than the left hand side, right? So there can be, as we have mentioned about these three different triangles. So initially 5G has started with these three different types of slices. So either you get a high broadband, enhanced mobile broadband, then you of course you have to pay. You tell that I have a VR game, I am doing a metaverse service. So you get you get a slice of this high speed mobile broadband. Then you have but if you are doing a V2V communication, or you are doing a remote driving, or you are doing some remote robot control, then you get another slice which is ultra reliable, which will ensure less bandwidth, but faster routing. Okay, in the earlier case you may not require faster routing, right? In the third case, it is machine type communication. Here, along with latency, you will also need very narrow band communication like NB-IoT, and along with that along with that, you will also try to ensure that there is a very low energy consumption. There is and but you are able to network operator is able to cater to all the sensors, so capacity becomes important. In case of enhanced mobile broadband, you may not require maybe not there may not be as many users who are doing a simultaneous metaverse operation or gaming operation. Again, the robot control will also may not be in the same category like the machine type communication. So depending on that, the network operator will reserve resources, and 3GPP definitely has all these guidances on how these resources are going to be connected, right? So um, what makes 6G different then? We are talking about AI native. Okay, so the rise of AI native is basically just to understand this analogy. A shark, a fish, you call it water native. It swims, right? A swimmer, a good swimmer, also swims, but you don't call him or her water native. So AI native and having AI in the network are two different things. Why? Because when I'm saying water native, that means it is born with all the traits of swimming through the water. When I'm adopting to water, then I need to, have a lot of overhead, and not everybody can do. Not all operators will be able to be, supporting AI infrastructure and all, because they have not grown it that way. Maybe they can hire some AI infrastructure and help. But this is the difference. Like, you start from the scratch, like how natively you embrace AI in every sphere. So 6G, if we delve a little bit deeper into it, as you will understand, as you have already understood from all, whatever we have discussed till now, 6G is looking from a variety of application perspective. There are many applications promised during 5G time. It did not work. They are now getting pushed to 6G, and now 6G has taken a comprehensive idea in terms of how cognition and control and twinning can work. So twinning means there will be a digital replica of a physical world. A factory may have a digital replica, right? And that needs to be updated. So that is why you will see sensing and communication has to go in hand in hand. And when you have sensing and communication together, that means you have to have some form of AI there, and because your physical world has to reflect in the digital world very quickly, then you need to have a very low latency communication, but still physics has some limit in terms of how far light can progress in 1 second. So of course there will be many AI driven aspects that will enable you, rather than sending the information, predicting the information, right? So there will be vertical application needs from society, from business, and based on that, the technology, the computing devices, digital services that will be, exposed. So AI is embedded natively across all layers. It is not like I deploy a network and I then add a computer to the network, and then I see, okay, I need to do, let me see how the data behaves. Let me see if I can do some kind of changes somewhere, what changes I need to do. Let the computer tell me. So that kind of intelligence is not there. It is the network itself, starts to behave intelligently, right? Network should be able to do real-time learning and decision making. It should be able to support digital twins, like, and holographic communications, and then seamless integration of physical and digital world. Now, the fundamental shift, as I have said, is 5G had been AI assisted, 6G is AI native. So in 5G, some kind of offline computation, like what should be the best scheduling policy, how can we predict the traffic, etc. Those can be assisted by adding extra AI bit. In case of 6G, the end-to-end network learns itself, adopts itself, and autonomously controls itself. We'll come to the point like why it is so. And it will be it will be deployed in physical layer, it will be deployed in MAC, in radio access network, it will be also deployed in the core network, and there are some other aspects also. And that aspect is there is an there are two dimensions of AI for AI/ML. One is AI for network. So AI/ML in every aspect of network, right? Which is from physical layer to your core network, everywhere you put AI. They should be AI driven. They should be able to adopt. It is not like today's physical layer or today's MAC layer where I know this is a protocol, this is a specification, and that is how I need to behave, right? And there are some predictive patterns, how the system will behave, and if there is a change, it is not able to cope up. If there is an additional load, if there is an change in the channel conditions, it will fail to cope up. And network for AI is the network itself will ensure that there will be infrastructures at the doorstep of the user equipment, so that low latency intelligence can be put to these infrastructures. So till date we talk about cloud native, and all our smartphone and everything, your Play Store, your any applications, everything, it runs on a cloud. So when you are developing an app for today, you expect that there will be cloud somewhere, and you design it that way. The change that we are going to have now, you're not getting the cloud, right? It is the cloud is provided. There are certain service providers like AWS is there, Azure is there, Google Cloud is there. They are the three big players. Then in China they have Alibaba and all. From there we are getting a shift towards edge native network, which is just as the network needs to run AI. So where will this AI reside? Okay, the AI is a computing algorithm, right? It has to reside somewhere. It has to store the data somewhere. Where does it store? It will store within its infrastructure itself. So there will be special boxes for computing. And very soon, maybe in 1 year or 2 years, you will see even Wi-Fi access points coming with computing power. So your home surveillance can be resolved in the edge itself, in the access point itself. So now the change that application developers can expect is that, while I used to think about that there should always be a cloud, right? And if the cloud dies, many application dies, because the application cannot run without the cloud. The same way, right now the trend is that with the advent of 6G, many applications which were cloud native may slowly switch to edge native networks. So that means just near your access point, just near your last mile connectivity, from where your last mile connectivity starts, you have a edge computing present over there, and the application designer can write an application assuming that there will be an edge computer which will give a very quick, very low latency communication or feedback to the user equipment, right? For whatever application it is looking for. So what is the timeline for IMT 2030? So IMT 2030 is basically the ITU terminology for 6G. So it started from 2021, and maybe we'll not see 5G in full, and we might get into 6G era. So that we might have very well a leapfrogging, because India is still using, largely is still using 4G, and 5G adoption is very less. One of the reasons is the promises of 5G that we have discussed so far. For several reasons, either they have not been realized fully, or there have been very little market adoption for that. So from 2021 to 2022, we already have gotten some 20 some agenda items, some charters. And then 2024, I was part of framing the study period 25 to 28 in World Telecommunication Standardization Assembly. And there we had the technical requirements, evaluation criteria, methodology, and everything. They all been formalized. From 2027, this is 2025, 2027, 2028, many countries will start to deploy this IMT 2030 vision, and by 2030 we should have the final specifications which will get deployed across the world. And with Bharat 6G Alliance and all, India is also trying to you know trying to cope up with the pace, and trying to define what really is going to be 6G. That the way, I mean, 6G, the way it will actually help us better to to improve the life and society of India. So it is very important that as researchers, as faculties, and as future thinkers, we think about the problems of the soil, and we try to understand, rather than mimicking what others are doing. We can think of what India really needs, what people of India really needs, what will actually benefit, the kind of applications that will actually benefit. Let me give you one very naive example, which is, if you think about the what has been the very recent times, what has been the extremely killer application for smartphones. If I talk about that, you will see that while TikTok videos and Facebook and all, that is one end, but for many people who were not fond of watching those videos, even in villages, okay, even seniors, many people are adopting smartphones for one killer application, which is UPI. Okay, so for to use UPI, you can't do UPI without a smartphone, the way the technology has been formed. So to do this kind of transactions, you have already the country is already getting used to this kind of transactions. And this is a definite killer application, which is for smartphones penetration. So similarly for 6G also, there are many visions coming from foreign countries and from different companies who are giving their own thoughts based on their business targets, their geographies business targets, the state of their economy. But this is also high time that we really think what 6G will really mean, and what is the problem that we really need to solve for India, considering the mass, right? And what is the AI? How AI is going to be useful when it comes to at our doorstep? If AI comes close to our base stations, how is it going to help? Now, since we are all mostly, I suppose, we are from electronics and communication background, and we must have all worked on the physical layer, physical layer stuffs. So let us take an example of what we really mean by AI for network, starting from the very basic physical layer. So physical layer, as we all know, is a fundamental, building block of any communication, so any communication system, and that is where actual physics starts. Okay, the physics of the media, right, and actual signal processing. On top of that, these are all logics. These are all not you won't find a lot of signal processing in the higher layers, right? These are all basically state machines. In physical layer, you have the raw signals, you have the raw bits, raw IQs. Okay, and you churn those numbers. So you perform modulation, demodulation, you perform channel coding, you perform equalization, you perform channel estimation, right? All these are very important. If any of these fails, then we have a problem, because then the signal, the later, the higher order layers will actually fail to work, right? So, what are the conventional techniques? We have channel estimation, we have linear estimators like least square, then minimum square, minimum square error. We have fixed modulation schemes like, oh, okay, if I am using 4G, it has few layers, right? It can at the lowest it can use BPSK, and then it can go for 16 QAM, then it can go for 64 QAM, then it can go for 256 or 256 QAM, like that. Okay, and the channel models, every standard built, they assume certain models, and they have certain very definitive models like highway model, rural model, then high speed model, and for that they assume some transfer functions, how the signal is going to decay, right? And so the signal processing is largely deterministic, even till today, even in 5G. So, and all this channel equalization and all that happens for considering pilot based technique is the most technique, and every modern communication system does have a pilot based system. So you insert a pilot from the transmitter signal, and then the pilot actually gets perturbed from the perturbation of the pilot signals at the receiver. You try to identify how much phase frequency errors and amplitude errors might have crept in, because pilot sequence is something that you already know. So it is a very a very supervised system. I know that there will be a pilot looking like this. I try to correlate, and if the pilot fails, then I know that how much, to what degree it fails. And the pilot signals are placed in front of the data signals in such a way that between the pilot signal and the data signal, the channel Doppler characteristics or the channel, the transfer function is not going to be that much severe, that between the arrival of the pilot or transmission of the pilot at T0 and transmission of the data, the channel has gone through a very very large change over that. That is the whole idea about pilot based communication. So idea is that if I know that the pilot have gone through this much of phase shift, this much of channel variations, then I just estimate the transfer function, channel transfer function, from looking at the pilot. And looking at that transfer function is directly deployed with an inverse operator to the data, assuming that a similar act all has happened on the data also. And based on that, the data is also tried, the IQs are recovered and the constellation is recovered. That is the common technique. I mean, even when I used to work on receiver chain, that is the fundamental premise of work that we used to do. But that has a limitation. The limitation is And that limitation you have to appreciate in terms of the scale at which 6G is going to work. You already have seen Elon Musk and all these people. They have started to, the Starlink and all. They have started to talk about satellite. So we are going to have a three-tier architecture in 6G. There is going to be all terrestrial networks. There is going to be airborne networks, and there is going to be space networks, right? So there are many attempts are being done, like Google tried to put balloons with connectivity, right? Balloons acting as base stations or access points. Then we had drones acting as base stations. We are even People are also talking about even aircrafts can at times military aircrafts and all for disaster situation may also act as base station. Okay, this is the vision, right? So there are short haul communications, there are long haul communications, and most importantly, there's a huge densification and huge diversity of the network. How it is, and it really becomes a nightmare for designers to predict a channel model for that, and to ensure latency and to ensure bandwidth, right? So you need to predict a channel model where you don't know where your device is going to be used. You don't know what kind of base station it is going to connect. You don't know what is going to be the backhaul. Is it going to be under the sea cables, or is it going to be satellite? So that is why this this huge complexity makes human in loop operations practically impossible, and deterministic models or typical rule based models practically impossible. Okay, because there can be endless number of rules, and that is where AI is sought after, because where you do not have definitive rule based if then else models, that is where AI has a role to play, because then it smartly acts. So existing systems have poor adaptability to dynamic environments. It also has higher computational complexity, although AI also has high computational complexity, much higher than this. Then, when there is non-linearity in the signal, in the channel, very limited performance gain, and you need a lot of manual tuning, design, and monitoring. Okay, and this we are talking about from the core network to to the physical layer, because every time your network configuration changes, every time the nature of the nodes that are contributing to the network changes, if a human has to monitor that and manually change the network parameters or arrange resources or even slices, right? The slicing that we have talked about. So it is not exactly like you build the road like that, right? You have a shared infrastructure, and the slice has to be defined in runtime based on the intent of the user. Okay, so in such situations, it becomes very difficult with traditional models, and that is why we are talking about AI, okay, across the network layer, right? So why AI is physical layer? So AI is offering a fundamentally different approach. So it is not relying on fixed models. It is learning from data. Okay. So you train that using the data. If you have data like this, it should be like this. If you have data like that, it should be like the outcome should be like that. Okay. So based on that, it adapts to real time, it adapts in real time, it can optimize performance, and it can even by itself discover, based on the learning, that what could be the new signal processing strategy, so that the transmitter does not always tell that your constellation should have a nice mapping of all the points lying here and here. That may be suboptimal given the channel condition. Maybe if your constellation is a little bit skewed, or if your constellation is a little bit, haphazard, with some points going down, some points going up, keeping keeping the total, power profile same, then what happens is that maybe it becomes easier to adapt the to rectify the error in constellation while receiving it. So the reduced need for manual design, real-time optimization, and it can learn complex mappings, like if this is the channel condition, what is going to be the constellation? If this is the channel condition, then, and if this is the IQ I have received, what could be the best, assumption for the IQ that had been sent from the other side? If this is the channel condition and if this is what user wants, then what can be the best constellation model, or what can be the best channel encoding model, right? All these things. So now, what are the some of the popular AI techniques? One is supervised learning. Supervised learning means that every data, you take the data point and you show you have a model, learning model, and you tell it that this is peer. If you see anything like this, call it a peer, and if this is banana, you call it a banana. So and it tries to find out, okay, there have been so many bananas I have seen, and it matches. Okay, let me call it banana, like that. Unsupervised learning is that you are not told what is there in the model. Okay, you are not told what is what. The only thing is that you are told is that you understand that, okay, so this is this has these features, that has these features, so this and that should form a common cluster, okay, or a common class, right? So it is almost same like in our aptitude questions, we are given like find the pattern or find the odd one out. You are not told what pattern you have to follow or anything. You can devise your pattern, right? So from your pattern, you just try to cluster out that who all can be grouped together based on one feature. And this can actually, this can actually change. I mean, if you look at the society can be broken or classified into many dimensions. I mean, sometimes you divide it in terms of in the name of race, sometimes you divide it in the name of religion. So these are all, classification algorithms that people apply while dealing with the society. Anyway, then we have something called reinforcement learning. So it is also unsupervised learning, and in this learning, so the model tries to, so model is not even clustering or anything. It is not even told that this is a cluster, that is a cluster. No, it is just told, okay, I get, I do something, I have found something. At every layer, it tries to say, am I doing it correct? Am I doing it correct? So it is just like a kid who has just learned to do, a little bit longer complex math, which involves multiple steps. So the kid will, for every step will ask the teacher, please tell me, is this correct? The teacher can tell, no, you have done this wrong operation. So the kid can get back, correct that step, again proceed further. Is this correct? The teacher says, yes, this is correct. So, okay, fine. Now, once this is done, this learning resides with the model, that is the kid. The kid understands that, okay, I last time I had this problems. I learned these models as this is this, so I can use it. So that is called reinforcement learning. And then comes the most modern thing, which is deep neural network. So you have an input layer, you have a lot of hidden layers who talk to each other, and then you have an output. So this hidden layer is something of a little bit problem also. But anyway, let us not get into that. So that is why we have convolution neural networks. We have recursive neural networks. We have transformers. Transformers are being used in LLM. and being used in a lot of other uh, LLMs and in Gen AI. Okay, all this, right? So now let us scroll through, like, how what are the different steps of in physical layer, what are the different aspects of physical layer through which this can work. So as you can see, this I have taken from Viavi Systems, from one of their publicly available white paper. So you can see how they are trying to change the complete physical layer. So there is a base station. So a base station is transmitting to a user equipment. So there will be LDPC encoding. Then there is rate matching, and after that, the before IFFT, the entire signal shaping is happening based on the channel parameters, and it is happening through deep neural network, right? On the other hand, so IFFT and AFFT is there because it is talking about systems related to LTE and above, which uses OFDM as a fundamental thing, or OFDM A, right? So IFFT, and then on the receiver side, it is doing FFT, and then it is trying to find log likelihood ratio based on the IQ from the log likelihood ratio. Rather than doing any encoding, decoding operation, you just simply pass it through some model, and which then gives you the decoded bits. Now, this is the vision. Okay, it is not that it has been it is not that it has been achieved so far. Okay, if this is something, someone can please go on mute. So it is going on. This is still a prevalent research topic. We still do not know whether it is going to work. Okay, but this is a vision. Given the complexity, given the changes, we have to see what is the reality. Okay, and that is the opportunity that we all have as researchers to explore. Then we have AI for equalization. Autoencoders are being are being tried for non-linear equalization. So channel equalization is inversing the channel effect, right? So in case of in the fading channels, the bit error rate performance, whether it improves, because fading does not really have any characteristics. You can model it using a relay, but relay fading is not something that is sacrosanct, because depending on the densification of the network, depending on how close, how neck to neck everybody is talking, and how frequent you are moving around, and and the given the wide nature of the geography that impacts your that impacts the shadowing, the 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 diffraction of radio, the scattering of radio. So from all these things, if it becomes so close, so narrow, you have to understand that when everything becomes so close, you are not able to supply as much power. You are going to higher frequencies because you have to give more capacity to the user equipments. You are going towards higher frequency. The more you are going towards higher frequency, your effective power that you can put to your signal is reducing. So the more you are reducing the signal power, the more it is, and it is in the higher frequency, it is more prone to fading, right? So that is why the autoencoders are being tried to see whether different form of adaptive equalization can be done. It can learn from the environment, and it can try to find out what is wrong. The other important aspect is beamforming. Beamforming is done even till today, but it is largely manual. Okay, it is largely manual because I mean the operator that sees that, okay, how many users I'm getting right now from such and such direction, so they manually turn the antennas to different location. I can tell you one A particular example, like when during the pandemic, all our offices were closed, and after pandemic, I went to one of the offices in Bangalore, and in Bangalore, in Whitefield area. And what I found was that just before the pandemic, where I used to get very good signal, I was not getting good enough signal. So what they said was that the antennas were all steered towards residential area, and that was a manual effort. Why it was steered towards residential area? Because people were working from there. So higher bandwidth was required from there. Otherwise what they do is that they during the office times they steer the antennas towards the population of the in the office area, because that is where bandwidth hungry exercises are being done, not in the residential area. So this is the kind of intelligence that you need to put. Otherwise you can't end up putting infrastructure after infrastructure after infrastructure, and they will end up interfering with each other. You will not have enough capacity. Now, given the densification of the network, given the close proximity of the devices, given the variation in the channel and the unpredictability, now it is highly important that this beam forming becomes completely without human in loop. Okay, the beams should they should learn from the channel. The multiple beams can be transmitted, and the receiver also, from its learning, can identify what should be the best beam for it to receive. Okay, which beam should give it the best signal, and that way all the antenna orientations can change. And this can also happen as a part of the slicing, because if there is an enterprise and the enterprise is trying to do holographic communication which needs high bandwidth, so what you need is the operator needs to ensure that that enterprise who has paid so much is getting a lot of bandwidth that it needs. And for that, what it does is it gives you the exact amount of beams that are required, the exact amount of bandwidth that is going to provide the SNR, okay, the required SNR for that kind of service. The other important aspect is intelligent reflecting surface. Now, intelligent reflecting surfaces are, I mean, by design, they're just dumb. They're just dumb radio reflectors. How are they intelligent? They're intelligent because they have these devices have certain hooks based on which the phase orientation or the phase shift can be optimized. Right now, who will put that intelligence? Either you can do it manually. I know one of the renowned institutes from India. They actually they actually demonstrated one such hardware, but then that was completely manual. So you manually configure the phase shifts, and that way the elements of the reconfigurable intelligent surface plate is oriented, and that is how the phase shift will ensure that all your users are getting the right kind of signal. But in a dynamic world, you're putting the RIS to or IRS to cater the user, but the user is mobile, right? So the phase shift cannot be static. It has to understand user behavior, and also there can be multiple users in multiple directions, right? It is not going to be a single mobile user. It may also be possible, and I see a lot of this kind of practical research are happening in Tsinghua and other universities in China. I don't know how much Indian academia is really doing in this regard. So multiple EVs need to have moving in multiple directions. So a single RIS plate serving each of the EV, okay, who are all moving in multiple directions. Now it needs intelligence. It needs not only intelligence, it needs lightweight intelligence, which you can run just on the RIS. Because one thing you have to remember, that RIS is not something that is, you know, that is like your normal base station. Your normal base station is connected via optical fiber to the cloud. It is connected to the server infrastructure. RIS is a standalone thing. It is a dumb thing, right? Until and unless it is excited by a incident radio wave, it can't do anything, right? So RIS has to be, modified. It has to have lightweight intelligence on top of it. I mean, one of my very close acquaintance professor in IIT Delhi is, uh, we are sharing some intellectual ideas also, and they are working on it, like how much lightweight intelligence you can put on the RIS controller itself, so that the RIS can behave smartly, and also it needs to ensure that the attack surface is reduced, because RIS should not be, those who are not allowed to send the traffic, or not allowed to get the signal, should not get the signal. Okay, so and it should also try to ensure that the signal does not pass through a potential eavesdropper or a potential malicious node, right? So that way the signal characteristics has to be molded and all. So RIS can no longer be a dumb device. There has to be an intelligent access control mechanism on top of the RIS, right? So uh, and also, like, how much boost you need to do, that depends on how many elements you have shifted towards the face, because it is all, collective energy going to one direction. So all these aspects are going in for intelligent reflecting surface. And then another very important and very crucial part of 6G, and in fact, all the physical and digital continuum, or whatever we are talking in 6G, is basically dependent on success of this technology, and it is also evolving, and still a lot of research of potential is there, which is integrated sensing and communication. So earlier we had as radio sensors, we had radars. So right now, radar frequency and communication frequency coming together, you need to sense while you communicate. So there has to be a composite waveform structure, a composite packet structure that will allow system to sense. Now the question is, why it needs to sense? It needs to sense for two reasons. One is, it needs to create a digital replica of the network itself. Why it needs to create a digital replica of the network? Because operators, when or policymakers today, how a network is going to behave, you cannot predict until and unless you actually deploy. Okay, that is a problem we are even facing in BSNL, right? But if you have a digital twin which exactly mimics the real network, then you have this beauty, which is, before you deploy, you convincingly simulate that entire environment, or sometimes you can even emulate on the real network, based on your twin, which resides in cloud, and it may even collectively reside in segmented fashion in your edges, right? That is from the network perspective. What is on the the other application perspective? When we talk about metaverse, when we talk about real-time smart city environment, the smart cities are going to live in a digital world. Okay, every city will have a digital replica. Why it needs to do so? Because if in tomorrow's cities, if you want to do a traffic planning, you need to understand what is the current form of traffic. What will be the result if I divert certain traffic in this way? What will be the result if today a procession is coming to the city? Okay, what should be the how should I arrange the traffic? The other thing is that in a connected vehicle setup, if your vehicles do not have drivers, they're all autonomous vehicles, maybe for specific purpose, maybe they're carrying some important stuffs, mails or whatever, or even it may be a automatic fire extinguisher car, which just gets triggered from the sensors that there is a fire, and it automatically starts to move without waiting for any human to operate there. It is not because human is not there, because you will not get that many humans, so it is trying to augment the human effort. Now in this case, just imagine the situation when a car is coming and there is another car is coming at the junction. How much speed should each car have so that they do not collide, right? Until and unless you have a holistic view of this entire environment, entire city, entire streets, and this immense computing, you are not able to compute the exact actuation parameters that you need to exert, right? So for this reason, we need to do sensing while we do communicate, rather than having additional sensors putting everywhere, because there is no end to it, right? So just like radar sensing, we not only sense the network, that we can sense from the network data itself, but we can sense using ray tracing and other techniques, which is co-located and intertwined with the communication network, to understand what is going to be my environment, or what is the state of my current environment. So every object gets replicated and their current status gets replicated. So I'm just keeping this. So these are some of the results. Now, what are the challenges? The challenge is that AI cannot work without data. Okay, whatever you are doing, supervised, unsupervised, you are doing CNN or whatever, every time AI will work based on, it needs data. Now, in physical layer, availability of data is a big concern because companies do not talk to each other. And this physical layer data is something that has not been preserved. It is not like your emails. It is not like your Facebook posts. These are raw bits. Even when I'm talking to you, the raw bits that are flowing through the Wi-Fi card of my laptop, right? And then it is going through my access point, then through the entire network. Who have stored these? These are not stored, right? What we store is the final data, the human readable data, but all these traces of data. So the emulating or simulating this data is also very important, and labeling that data, this is very crucial. How companies are working? So companies are currently either they are using their standalone infrastructures or they are still simulating. If you want to do some work, you can do some work in the here. Then AI models, different companies, different institutions, they're doing, they do not interoperate. So today, I use, suppose I use a phone from, say, uh, Samsung or LG or Nokia or Siemens or whatever, whatnot company. You are using another phone. The base station is coming from another vendor. The network infrastructure, maybe Cisco or Huawei or any other company or Tejas from India, they are providing network operator, maybe Vodafone, maybe Airtel, maybe Jio. We don't care. We all talk to each other because we are using an interoperable standards. But tomorrow, if AI models do not talk to each other, then this becomes a problem. Things will not interoperate. Okay, and AI has a stringent hardware constraint. So lightweight AI, if you want to do modeling, it's still fine. Inference, can you do it lightweight? Response time, at times, initially, AI will take some time to respond. So for highly, dynamic systems, highly agile system, will AI really respond in time, or will you still stick to the predictive system? Even there is, till date, there is a significant quarter of physical layer researchers, physical layer, engineers, physical layer businessmen, business organizations who still believe that probably we're still far, far off than relying on completely on AI in the physical layer, because predictive models may work much more better. But this is something to evaluate. Even if to say that it does not work, is a good amount of research with a good amount of data, right? And security is definitely a concern. The other thing is that I have not mentioned here is the explainability. So AI has a problem, which is that unlike conventional deterministic signal processing, uh, or rule-based systems where debugging is somewhat in philosophy straightforward. You know that this after this step should behave like this. If the previous step has got this input, the previous step should giving that output, and this step should taking that output and giving this taking that input and giving me this output. It should be like this. If it is not happening, then at one point or other, you can zero in and you can debug and you can fix the system. In case of AI, especially in case of deep neural networks, this is very difficult because explainability is something you can't really, it is still, it is now a very popular subject in computer science. So so the point is that if in telecommunication there is very narrow margin of error, okay, the way systems are synchronized, there is very narrow margin of error. So if you are not able to, if something is going wrong and the engineer who has deployed it is not able to explain, then it's a mayhem. The entire system goes down. So there is a lot of skepticism on using AI for this thing. But AI is being practically used for many systems where it is used for debugging and all, right? I've got 7 or 6 more minutes, so I will quickly touch through another paradigm, which is network for AI. So it is like, just let me see if this video works.
Yeah. Okay, let me introduce Fulvio Fugazza. It's our account director from SecT, and together we have been defining this demo in order to show you the potential of 5G. I hope that...
So this is a video that I captured in 2019 when I was in Valencia, and this was the world's first ever, holographic communication. If you see, the green person does not have a shadow, but the black person has a shadow. So the green person is actually not present physically. The green person is 5 kilometers away from the conference venue, right? And the black person is the host. So this is called holographic communication. Now, this was in 2019. The pace at which technology is progressing, this is 2025, right? Almost we have passed the first half of 2025, and we're moving towards, fast towards 2027. We're talking about IMT 2030. Why is this not yet popular? We don't see this popularly in our day-to-day practices. Why is it so? Because you need to ask as engineers some fundamental questions which have been put by the invention of radio by J.C. Bose, and the other one is Claude Shannon. It is all modern communication system is limited by two things. One is how quick electromagnetic wave can propagate, how far it can propagate, okay, and of course it has decay and all these things. But assuming a vacuum, in 1 millisecond light can only travel 300 kilometers, not more than that. So worldwide communication is definitely a problem, with this kind of latency, okay? Because if you look at this video, you can see how these people are communicating.
Let me introduce today here, please. Yeah. So this
You see,
explaining the technical strengths of 5G behind this demo that we are seeing today here, please. Yeah. So this.
So you can see how the latency is minimal. It appears like that person is there. They could do it because I checked with the engineers. They could do it because they had a terahertz link, point-to-point line of sight link between two antennas for 5 kilometers. But think about stretching this beyond 5 kilometers, stretching this across hundreds of miles, right? How can you really do this? And of course, you just try to imagine what is the bandwidth required. I mean, when you are giving this service, it is not a single person is going to do this service, a single person using this service, right? There will be a lot of technologies that a lot of enterprises that will be using this service. Just like right now, I am having this video chat and audio video conversation, and maybe there are thousands or thousands other people might be doing audio video communication right now, but still the computing infrastructure is able to hold that tight. Okay, it is not melting down. But with this kind of infrastructure, is Shannon's limit going to be supported, or Shannon's limit is going to be challenged heavily, right? And under such situation, can you guarantee the KPIs? Okay. Now that brings us to the typical problem of, rather than technically solving communication, the telecommunication, can you put it in a semantic problem, which is I don't share the exact information, but I give you certain clues of the information, and as a receiver, you generate that information, okay, at your end based on your knowledge base. For example, I give an example of the newspaper. So suppose some incident has happened at some place. A reporter is watching that and creating a news report, which is getting printed in the printed form, in a textual form, and that textual form, that newspaper is being delivered to you in the morning. You are reading that newspaper, you are not visualizing what has happened, but in your brain something is visualized. And the beauty is that the effective communication is that through the semantic representation of what was presented, what happened at the other end, that semantic representation is actually creating a similar kind of inference. So you are getting the main message is being given to you, right? That some person has hit somebody, or Sachin Tendulkar has hit a six. That is what is important for you, right? So that gives us to the paradigm of the when we talk about metaverse, we talk about holographic services, we talk about massive IoT, we feel that although we can make a lot of advancements in physical layer, we can make a lot of advancements in core network, there will still be rooms, there will still, there will be a limit till which you can actually provide with the based on the current physics of the technology. So the idea is switching to semantic representation. So you don't send the entire video, you just send some clues on the video and you try to generate that video. A lot of research is happening on this. Is you still have the channel encoding and decoding, you still have Shannon's formula, Shannon's theorem, but what this channel encoding and decoding is transferring over the physical channel is not the exact information, the exact video, exact audio, or anything. It is transferring the inference, the semantic information. So the bandwidth usage becomes very less. So it can actually be as less as, so a 8K video can be represented in just 1 kilobyte of data for each frame, right? And from there you just regenerate, and that is why GenAI and all have a renewed interest in telecommunication. But one thing is that you must have a shared knowledge base. So when I say earth, so the sender has an image of earth like this, the receiver has an image of earth like this, then it's a problem, right? Both must have a similar kind of understanding, then only we can generate the similar kind of data, and we can then circumvent Shannon's theorem. Now this is a curated video, a demo of how semantic thing can work. We did this about 2 years back in our lab in Calcutta. And just a minute. So this is just a hardware, telepresence hardware. So we use what we are doing this here is basically I am demonstrating a robot, and this robot is being, there is a identical robot in another lab, and there is a digital avatar who is being observed by the person wearing this holographic glass. And whatever I am doing, this avatar is mimicking, right? So then you are getting this entire 3D presence of the person here standing here. Now, of course, this can be more human-like and all. This is just a prototype. And again, this was done offline. So first, the AI was applied to get the body junctions, body parameters, and it got applied on the avatar. Okay, so that way it works like this. This is the and this is how AI for network is going to work. So what you have is that you are sending only your data to, only your video, your high definition video, only up to the base station. And there, your body parts are getting extracted, and this becomes only a few bytes of data, and that data is getting deferred here. The challenge is that sending the data over here in real time, and within a stipulated time you have to get the body joints extracted from here, right? And this is a big challenge. This is a big challenge. Otherwise it cannot, this kind of system cannot work. So in the interest of time, I'm not showing you the real practical experiments. And with this, I thank you for your patient hearing.
Thank you, sir. Thank you for your interactive session, and very much informative it was. And this is for question answer session. If anybody want to ask sir any questions regarding this topic, please feel free to ask him. Do you have any questions, anybody? Okay, I think anybody don't have any questions right now. And thank you for your informative session, sir. And we have got lots of information in implementation of AI in next generation communication. So, sir, we have a token of greeting from our institution, Dr. Sudhi Chandrasur Engineering College and Sports Complex. This is a small memento for you, sir. Please kindly accept it.
Yeah, thank you.
We'll send it in your mail very shortly, sir. And thank you, sir. Thank you for your session. And thank you, everyone. And our next session will start shortly now. And